Thank you, everybody. I hope that you enjoyed tonight's lecture. The title of the lecture is The Broken Plate Beneath the Cascade Mountains. And you're like, what? It's like a tectonic plate, a broken plate. And you're like, well, that doesn't sound good. Should I be worried about that? There's a broken tectonic plate? What are we going to do about this? It's okay. There was an oceanic plate that was broken 50 million years ago because of North America colliding with an oceanic island. And that collision broke the plate, and shortly after that, the Cascade volcanic arc got established. So this is a Cascades volcano talk. This is a geology talk. I don't know if you're in the right auditorium, but this is geology that we're doing tonight with chalkboards and with images. But it's this broken plate story that is brand new to me. I've been teaching about the Cascades for 40 years in my geology classes, and I didn't know about this broken plate story. And there's exciting new data from the rocks of the high Cascades that have some detail that we just didn't have before. And so with all this detective work, up in the high Cascades with granites and lava flows, high and low, we've been able to put this story together of an ocean plate that broke and is now down underneath a portion of the Pacific Northwest. You'll even see an animation that was custom made for us before we quit here tonight. So there's many geologists who have contributed to this story, and I'm a teacher. I don't do any of the research. But in this room is University of Puget Sound geology professor Jeff Tepper. He's right there. And so Jeff and his students have been working on much of this data for the last 25 years, and the papers are now coming out. And so I'm excited to share much of Jeff's work with his students, among other people as well. Let's go. So let's say you're watching this from a long way away, or you're brand new to the Pacific Northwest. Here's a map of the Pacific Northwest. Here are the Cascade Mountains. It's a north-south trending range. It separates eastern Washington from western Washington, the dry side with the wet side, the 509ers with the 206ers. What? Okay, yeah. So that's the mountain range we're talking about, and there is a trench offshore with a subducting ocean plate. And the most famous aspect of the Cascade volcanic arc, yeah, it's a volcanic arc. Let's even draw that. Let's even write that. This is a volcanic arc. We're going to use that phrase arc a lot tonight. And an arc simply means a line of volcanoes that are the result of a subducting oceanic plate offshore. Good. Arc volcanism. We learned last night that the Cascade volcanic arc started 46 million years ago. 46 million years ago, and it continues this evening. It's still active. There are beautiful cones on the horizon. Now, if I have to do a basic geologic cross-section of the same thing, I can do that pretty quickly. It's no sweat. I can do it in my sleep, I think. This is a collision between two oceanic plates. No, an oceanic plate and a continental plate. The thin ocean plate dives beneath the thick continental plate. There's magma being generated above the subduction zone. And in Geology 101 land, I would simply say these Mount St. Helens, Mount Rainier volcanoes are made out of the rock called andesite, Geology 101. And that if we eventually cool off these magmas and make plutonic igneous rocks underneath the Cascade volcanic arc, we're going to make an igneous rock called diorite. Intermediate magmas, 60% silica, middle of the road, some sort of mix of oceanic and continental rocks. That's Geology 101 country. So we're starting with some simple drawings and messages to just involve as many people as possible in this room. If I go over here to the little black chalkboard, I can draw what's behind you, and you will see this walking out this auditorium to your cars tonight. In the twilight, you will see a rugged, jagged skyline looking west. So Ellensburg is here, so looking west at the skyline of the Cascades, you'll see that rugged landscape. And above that rugged landscape are these impossibly perfect cones. The cones are the famous Cascade volcanoes, Mount Hood, if you like, Mount Shasta. And those cones are less than 1 million years old. We did this last night. So we're not going to pay attention to those cones because we're talking about old history tonight. Tonight we're going to talk about two stories that we can pull from these rugged landscapes. They're in the Cascades, but they're the older portion of the Cascade volcanic arc. One of the stories is 51 to 48 million years ago. And the second story is 46 to 0. So the 46 to 0 is the arc, and so our broken plate story is going to be happening here, 51 to 48. What kind of evidence do we have that Jeff and his students have been looking at? There's a renaissance, there's a rebirth, there's a renewed interest in some new data sets. One, we can get some much more precise age dates than we could before, a generation ago. Two, you can get to some fancy instruments easier these days and cheaper these days to run geochemistry samples of these Cascade rocks. And three, there's another data set that can look down in the mantle and actually find a broken plate that used to be at the surface and is now down in the mantle of the earth. Tomography, it's called. So all three of those collections of data are what we're using tonight with this story. It's a detective story, essentially, to find this broken plate that's beneath the Cascades. Okay, simple, simple, simple. Let's add a little bit of detail now. Nice and big, nice and big. With this Cascade volcanic arc, or any volcanic arc worldwide, you see how quickly I can do that? No big deal. If I'm feeling perky one particular quarter on a good day and I'm teaching Geology 101 and it's a good group, I'll add more than this. I'm kind of moody that way. So then I'll go, there's a little bit more we can say about these arc magmas. Number one, if you look at some of these magmas and you look at some of the minerals, students, inside of the Cascade rocks that are in the Cascade volcanic arc, you can look for black minerals that are long and thin. That mineral got out of the rock for some reason. So there are black minerals, many different kinds of black minerals in igneous rocks, but the hornblende minerals are long and thin. There's two cleavage planes at 60 degrees between the two cleavage planes. It's a shiny black mineral. And in these volcanic and plutonic rocks, if you can find the mineral hornblende, Hornblende, squeeze it in there. These black pine needles in that igneous rock is a strong vote, not a smoking gun, but a strong vote for a subduction-generated magma, an arc magma. So we're looking for hornblendes, I say in Geology 101. What I don't say in Geology 101, but I'm going to start doing it next time I teach it, if I get to teach it again, are rocks that also are from the Cascade volcanic arc, whether they're plutonic, magma chamber rocks that formed underground, or volcanic lavas that came out of an erupting cone volcano. We can find black rocks, I know that's white, but black rocks inside of a salt and pepper granite. Do you know what those are called? That's right. These are mafic enclaves. I didn't know anything about mafic enclaves, Enclaves. I thought anytime I saw a black rock inside of a granite, I assumed it was just a black rock that kerplunked into this magma chamber and didn't totally melt as that magma was nice and hot. It was a xenolith. It was a big block of black rock that didn't assimilate into the chemistry of the magma. I was taught from Dr. Tepper this past summer that if you look very, very carefully at some of those black rocks inside of the granite, look at the edges of them. I can't do it well with my chalk, but the boundary of these mafic enclaves are not a sharp boundary. They're kind of a fuzzy boundary. These black things inside of the granites, these black things inside of the lavas sometimes, are kind of a ghosted outline of these mafic enclaves, kind of a fuzzy outline. And if you get on your hands and knees and really look at some of these mafic enclaves, I'll show you some pictures in a second, there's fluid exchange between the black rock and the surrounding white rock. And it becomes clear by looking at the textures and the geometries of these mafic enclaves within this igneous rock that there's actually fluid exchange, and both things are fluid. It's squirts of Hershey's chocolate syrup into some sort of light-colored oatmeal. They both have some fluidity to them, and we're getting all sorts of mixing with the mafic, the black, and the oatmeal, the lighter-colored stuff. That's a long way of saying that these mafic enclaves are also a strong vote for a subduction zone system. Mafic enclaves and hornblende, a telltale sign of some of these arc rocks. I'm setting you up for something, obviously. Okay, it's time for us to kick it up a notch. That was the simple portion, okay? And that's simple enough for my brain. Now I got to work a little harder to keep the pace going, but to get to the notes and realize I need to do some fancy stuff now. In Geology 101, I would simply say this magma is coming up through North America's basement, and I would just leave it alone. But many of you in this room know that if you study the basement rock of the Pacific Northwest, in Washington in particular, there's a lot of different kinds of rock: metamorphic rock, sedimentary rock, igneous rock, of different ages, of different origins. Some of the basement of North America is from the Pacific. Some of it's from the Arctic. It's bizarre, exotic terrain type stuff. So that's important to mention here, and I want to do this quickly, that if I get off of my simple sketch from Geology 101, and we now realize that if we're talking about Washington, and we are, and we're talking about Seattle on one side of the Cascades, and Ellensburg on the other side of the Cascades, can I cartoonishly show to you 4 subsets of the basement of Washington? I'm going to try something like that. This is Siletzia, which we'll factor in later today. That's the oceanic basalt that was offshore of Washington and got added 50 million years ago. This is, I'm going to write it, but it's going to be too small for most of you to, I'll do this. Melange with a little, melange, that's French. An Arkosic melange, colored grello from the Cascade alphabet that we did this past winter. This melange is interesting unto itself. I ignored the Arkosic melange, or the melange belt, the western melange belt, the eastern melange belt for a long time because I didn't understand it. That's my strategy. If I'm confused, I just move on to something that feels better. But I eventually understood that this melange belt is very important for understanding Cascade geology because, please note, once we generate some magmas somehow in our subduction zone, in our arc setup, we're going to have a bunch of that magma come up through the melange. The melange is a mixture of rocks. That's what the word literally means. And in the case of our Arkosic melange, there's an Arkosic sandstone matrix, and inside of this melange are enormous blocks of gabbro, of gneiss, of limestone, and the origin of those blocks of big things are literally across the Pacific Ocean. So, imagine yourself being an arc magma trying to get to the surface, and you're eating your way through this dog's breakfast, this amazing variety of bedrock within one unit known as the Western Melange Belt. Finishing the crystalline core. You'll see some photos in a second. Gary Paul photos will be featured again tonight. And the Swak Formation. The only thing that's local, the only thing that's native, is the Arkosic sandstone of the Swak. In other words, everything else, asterisk, 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 everything else was brought in from elsewhere. And you're like, tell me more about that. That was last night. Okay, that was last night. We got it here now. And 50 million years, between 60 and 50 million years ago, there was a low, broad plain, we think, not many mountains, during the Swak Formation time, 60 to 50 million years ago. And if some of you know the Bellingham area, that's the Chuckanut sandstone. So the Chuckanut and the Swak are the same stuff, separated by the Straight Creek Fault. So we have 4 constituents within this basement unit. And it's the melange that's going to be the biggest part of our story. Oh God, am I really going to talk about this? Yeah, I think I am. Okay, hang on. When we have a volcanic arc and we have subduction, we have a mantle wedge. And a mantle wedge is just like it sounds. It's a patch of real estate down here that is wedge-shaped, that's below the crust and in the upper part of the mantle. And so as we drive our oceanic plate down the subduction zone, if we pull, as we slab pull, as we yank on the edge of this thing weighted by eclogite, and we have this thing come down deeper and deeper, I'm still setting you up for the major broken thing. We haven't broken a plate yet, by the way, if you've been waiting. Okay, it's coming. Second half of the chalkboard stuff. So as we pull this ocean plate down, the pressure increases and there's seawater in the ocean plate material. So eventually, as we get deep enough, we are going to drive water, seawater, out of this downgoing ocean slab and add the seawater into this mantle wedge. That's truly where we're generating these magmas. So in Geology 101, if I'm lazy, I just say, oh, the ocean plate melts and then the stuff comes to the surface in the form of the Cascade volcanic arc. Not true. We have all sorts of detail now to say that the magmas are forming in the mantle wedge, and they are mafic, they are basaltic, they are runny, they are low in silica. Everything's starting as a basaltic story down here in the mantle wedge. And then, now that I've given you the detail about the melange, you can remember it, even though I just erased it. We're going to inject that basalt into the base of the crust, and it's now coming up through this Arkosic melange, this mixture of bedrock. So we have crustal assimilation, we have all sorts of evolving of the magmas chemically, and by the time we get to the surface, we've got a whole range of possibilities. It's time for a quick igneous rock classification chart, everybody. Don't leave yet. You can't wait for this, I'm sure. If we have an arc system and we have originally basaltic material, but we're sending it all the way to the surface, it's more complicated than just andesite. An igneous rock classification chart from an igneous rock lab room, it can be Geology 101. BADR, basalt, andesite, dacite, rhyolite. This top row are a number of volcanic rock layers that are erupting out of the volcano and onto the surface. There are plutonic or magma chamber equivalents down below. I'm leading to a point. Gabbro, diorite, tonalite, granite. Those are magma chamber rocks. And I'm saying that whether you're in a volcanic system or in a magma system down below, all of these compositions are not only possible, they are common in a volcanic arc system. It's not just andesite. We go from 45% silica all the way up to 75% silica. All of these compositions are possible because of the evolution of this magma as it rises, the assimilation of the bedrock of different types that these magmas are coming up through. Energy is so good in this room. Thank you so much. Yep. So I'm following the numbers here. This is now 7 and 8. I've made a little road map for myself, and I'm 8. I'm not looking forward to 8. I'm on 7, okay? 8's going to be on the blackboard. I need to be psyched up for that. Okay, switch it up. Switch it up. Washington. Oh, wow. Oh. Good. So this is the state of Washington. Here is Seattle. Here is Spokane. Ellensburg is here, where you are sitting in this auditorium. Portland, Oregon is down here. This is Oregon. Oregon, Washington, British Columbia, Vancouver Island, Idaho over here. We good? Washington. And we're talking about the Washington portion of the Cascade volcanic arc only tonight. I'm Washington-centric. I'm sorry. So if we outline this broad Cascade apron, and we know that we have 46 million years worth of arc magmas coming from a mantle wedge and rising to the surface, and having all of these compositions, basalt, andesite, dacite, and rhyolite, we can expect to find a parade of plutons within, what's the dots? It's the basement. Correct. The Arkosic melange is the host rock. We have a big broad belt. Of course, you don't remember. I erased it. Right? The melange is there, and we're having these arc magmas come up through this Arkosic melange. We now have geophysical data. I learned that this winter as well, that if you squint and look at those images indirectly of what's in the basement, even if we have volcanic cover, there's good indication that that Arkosic melange is going all the way down to the Columbia River Gorge and beyond at the deepest level. So we have this nest of Arkosic sandstone, the melange, and all of these arc magmas coming up through. We'll look at some slides in a bit, but Tamanous Rock, Granite Falls, Index Pluton, Squire Creek Pluton, I'm stalling, Tatoosh, Spirit Lake, Cispus, whatever, okay? Yeah, there's a lot of arc magmas, and it's not just at one time. We have 46 to 0 million years old. So all through the 40s, the 30s, the 20s, the teens, and the aughts, by decade, we have all this stuff. But the point is, they're all being generated with this arc story. The magmas are all starting down at the mantle wedge. We have all these possibilities, and we've been focusing only on this portion of the story, which is the most familiar story. Now, what am I dreading drawing on this blackboard? Anybody want to guess? That's right. Trace element geochemistry. Here we go. Let's do it. All right. So Hannah Shamlu sat here last night, and so I set this board up here in case I needed help. Now she's way the hell back there, so I'm on an island tonight. I think I can do this. So if we look with this new instrumentation, it's much easier and much more affordable to get this trace element data. What I want to plot for you quickly is geochemical data, trace element geochemical data that confirms the arc story. And all of these plutons, all of these volcanoes, everybody being generated in this arc factory is going to have a similar looking trace element geochemical plot. What do they look like? This is the reason I'm nervous. I didn't know anything about this till about 2 months ago. And I got a lot of help from Jeff Tepper and Hannah Shamlu, the two geochemists in my life. So we're going to have arc here, and we're going to leave this one alone for right now, but obviously that's the broken thing we're about to get to. Okay? Morb, M-O-R-B. A morb is a mid-ocean ridge basalt. And the standard way to plot this trace element geochemistry is against a morb basalt. In other words, looking at a common basalt that's formed without subduction, that's the vertical axis. The horizontal axis is a number of trace elements that are commonly found in these rocks. I'm only going to focus on a few. Can I do it from memory? Barium. Thorium. Oh, the hush in the room. I just said one word. If you want to stop a crowd, you just roll out tantalum and niobium, and everybody's just in seventh heaven. B-A-T-H. Good thing I did yoga this morning. Crouching beautifully. Crouching tiger, hidden dragon. The only thing I'm leading to that I have learned is that if you plot the barium, thorium, tantalum, niobium among the other trace elements, there is a plot compared to Morbs, wait for it, of a dramatic valley, a peak next to a valley, meaning there's not a whole lot of tantalum and niobium in those arc rocks compared to the amount of barium and thorium in those same arc rocks. If you're getting lost, maybe I am too, but the idea is you can collect wherever you like. Mount Rainier, the cone, Tatoosh Pluton beneath Mount Rainier. Spirit Lake Pluton, you can pick up pieces of Mount St. Helens. You can be up north, Mount Baker. You're always going to find this look, if it's a true arc signature at the geochemical level, a valley at tantalum and niobium. And you're like, who cares? Well, we're obviously setting up this discovery. And the discovery of this broken plate ties into all of this stuff I was just presented to you. It's like this whole buildup of 30 minutes was to get ready for right now. And I can go quicker now because I've laid all the groundwork with you, and I feel comfortable now that we can do this. Okay? So, there's another story. What's the other story? I lost it. I just erased it. But it was the 51 to 48, correct? So I'll redo it over here. Get rid of John Stockton. We got 51 to 48, and we've got 46 to 40. Sorry, 46 to 0. So this is our arc story, which we've established now. I don't need to beat it to death. But for the rest of tonight, at least with the chalkboard, we have something called a Breakoff belt, discovered first at White Pass with the basalt of Summit Creek, a bimodal collection of rocks. I'll explain. And those bimodal volcanic rocks were in this age window. So if you're just taking a few steps back and you're like, how do we know that the Cascade started 46 million years ago? One way to answer the question is the signature of the arc magmas that we have in the Pacific Northwest are all in a line, and they can be found with all these compositions and this trace element plot. And we go back to 46 million years ago, and that's consistent. But if we go back 48 to 51, we lose the Niobium Valley. We lose BADR. We just have B and R. That's what bimodal means, by the way. Am I losing you? So this bedrock in the Breakoff belt is older. We've got the precise ages now. It's weirdly linear. So this racing stripe down the middle of the arc is not part of the arc. It's older than the arc. You with me? This is the original Breakoff belt between 51 and 48. And you're like, what do those rocks look like? They're bimodal. They don't have andesites and dacites. They don't have diorites and tonalites. They're bimodal. They're two different ends of the spectrum. There's brown to black lavas that are basalts. There are pink rhyolites that are found collectively. You're like, okay, where are we talking about? The Cascades. Give me some specifics. I'm pointing north. The Teanaway Formation is not far from here. You know that there's some gold mines at Wenatchee. There's some gold mines at Liberty. You know that there's some beautiful Ellensburg blue agates. That gold and blue agate stuff close to Blewett Pass is the Teanaway Formation. It is bimodal. It is part of the Breakoff belt. So some of the evidence we have for this broken plate is that frickin' stuff right over there by Lake Cochise. Right above Lake Cochise, you can see it driving I-90. And the smoking gun for us geochemically and why we care about these trace elements is that we plot the same trace elements against Morb, and we don't have a valley with the Breakoff magmas. We don't have the tantalum, niobium valleys. And you're like, I don't see why. All this stuff works together. And all this stuff working together tells a convincing case that we have a broken plate down below. And you're like, I don't think I see that. Wait, there's more. Yep. Good. So how do we explain, before the Cascade volcanic arc gets established, a breakoff belt? What is our tectonic model to explain that data? The basic idea is that if you have magmas that are bimodal, and we have our bimodal magmas, that's what this is, with no niobium valleys, and I'm saying that those rocks are found in this linear belt, that's the challenge. How do you explain something like that? Well, the geochemistry in particular suggests that there is no slab beneath this area between 51 to 48 million years ago. Okay, well, let's slow down and see what that means. If we don't have this descending slab, we're too early. This is 51 to 48. We're not to 46 million years yet. This sure as hell looks like a broken slab to me. Yeah, that's what we're trying to indicate. And if we have this broken slab and there is missing slab beneath this area, that means that mantle, hot mantle, which is solid, is able to slowly but surely move towards the surface where the pressure is less. And we have less and less pressure as we have this hot mantle getting shallower than it should be. And we start generating magmas not from adding water. We don't have a slab. We're not driving the seawater off like we had in the prior sketch. This is a completely different way to generate magmas. These are decompression magmas. This decompression melting, allowing these bimodal signatures to come to the surface, basalt and rhyolite, but nothing in between. Even with the slides, we're going to have a detailed explanation about why this valley is present with arc magmas and not with this, courtesy of Chris Mattinson from CWU. So to finish the chalkboard session, why is this happening? Why are we just suddenly taking this ocean plate and breaking it? And the answer is, do you remember, we had a large island called Siletzia, which was built quickly of basalt off the coast of Northern California starting 56 million years ago. And that Siletzia, large igneous province, which was straddling a spreading ridge, by the way, got closer and closer to the edge of North America. And the edge of North America at the time, in the neighborhood of 50 million years ago, was Seattle. There was no Olympic Peninsula. And you're like, really? There was a time when there wasn't the Olympic Peninsula? Yeah, this is the Olympic Peninsula. It's coming in, man. The addition of Siletzia builds much of the bedrock of the Olympic Peninsula. So when we finally bring this thing in and dock it, the ocean plate that was tied to Siletzia is starting to have a problem. Because this portion of the Farallon plate is tied to Siletzia, and Siletzia is clogging the trench and not allowing this portion of the oceanic Farallon plate to do its subduction story. And so a portion of the plate that was there is going to break off. This is the broken plate from the title of today's lecture. And the weighted end of this broken piece of the Farallon plate starts sinking. It's going to start spinning in the mantle, and we're going to have something called rollback magmas, which you'll see visually with the slides in just a second. This whole story, which is pretty easy to follow, I think. You have a docking oceanic island and a broken plate and a gap that develops. This is the Breakoff belt. Is only possible to visualize with precise ages, with trace element geochemistry, and tomography. because the last point is, over here in Idaho, in the subsurface, not at the surface, but in the subsurface, is a vertical slab of ocean crust. This guy is now here, underneath Idaho, known as the Idaho slab curtain. And when you look at the Pacific Northwest, he can't stop, by the way. I thought I was wrapping up, but I forgot I wanted to show you this. If we go back to we have to get rid of the volcanic arc now. We're breaking the plate, right? That's preceding the 46 million year old volcanic arc. So get rid of it. If you feel like this trace element geochemistry stuff and the BADR and the bimodal is like, whatever, the igneous geologists, I don't know what they're saying. I can't understand those plots. Well, maybe this works for you. The suture where Siletzia adds to Old North America, and the Breakoff belt, which we don't know if it continues down to southern Oregon because there's a lot of younger lavas, but let's just go ahead and play. And this Idaho slab curtain, which is this piece of ocean crust that's now in the mantle hanging below the state of Idaho. Is this a coincidence that all three of these things are parallel to each other? Jeff Tepper and his students see this thing working together. Courtesy of Ken Clark, University of Puget Sound, we have these fantastic handmade diagrams. Let me just give you the whole story in proper sequence. Siletzia offshore. Farallon plate brings Siletzia to us. We dock Siletzia. We crumple the old west coast of North America. There's some local deformation. Uh-oh, we've got a break. We've got a break on our hands between 51 and 48, demonstrated by all of the data that I shared with you tonight. After we break, the portion that broke is going to do some weird kind of gymnastics, which we'll look at courtesy of the animation coming in a bit. But now the leading edge of this broken piece is descending, and this is the beginning of the Cascade volcanic arc. And by the time we get that proper depth to this downgoing ocean slab, we start making arc magmas with hornblends and mafic enclaves, just like we're doing this evening. This past winter, I did a series of live programs, 26 of them from A to Z, and we broke out these individual chapters by color to work our way through the history. And today, we're walking still in blue with our break time. And if you come back tomorrow night, we'll be thinking more about the brown and yellow time and some of these younger stories within the Cascades. We're going to make that arc first. We're going to do it in reverse order. Since the arc is fresh in our mind, is that right? I forget what I did here. Hang on. We got the arc. Yes, we're making the arc in the basement. We're making these magmas in the basement. And now we've got some custom maps from Tom from Maple Valley, who's here tonight. We're going to look at his beautiful artwork, and we're going to see that there's a major difference between the basement of North America and the basement of Washington that's exposed north of I-90 versus south of I-90. So north of I-90, we have the fruitcake, as I used to call it, the exotic terrain bedrock that's right there naked at the surface. And in between those majestic stratocones like Glacier Peak Volcano and Mount Baker, we have exposed bedrock, basement rock, exotic rock, Glacier Peak, surrounded by Chewacam schist and so on. But if we then go south of I-90, down between Rainier and Adams and Mount St. Helens, there's a lot of younger cover that I'm showing in green that's concealing the fruitcake. So we have to rely on geophysics to help us understand what the bedrock is down there. So backcountry Gary Paul with some fantastic photos of some of the South Cascade cones. Yes, a major boundary, which will come up again tomorrow night if you come back with us. But that old crystalline core bedrock rose quickly in last night's lecture, but here it is. That's a portion of the bedrock that makes up much, not all, but much of the North Cascade scenery. It's tough, old basement rock, crystalline core with all sorts of exotic terrain stories going back more than 100 million years ago. But what's important tonight is Arkosic melange. Are units that are a mixture of sandstone and other god-awful things that are all swirled together in a blender. And you'll notice what this is. This is Mount Si, right above North Bend. That's part of this melange belt. Mount Si, again, different look going across the valley from Gary. This is an important unit when understanding what's really truly at depth beneath much, not all, but much of the Cascade volcanic arc. Gary gives us this as a nice visual for the enticing mixture of colors, textures, and origin bedrock that's in this Arkosic melange. So it's all there preceding the two chapters that we're talking about tonight. This is going back hundreds of millions of years. And if you must know, this grello, as we were calling it, a mixture of gray and yellow on our maps, is helping us see that there's a bunch of this stuff. So here's Snoqualmie Pass and I-90. Here's US 2 going over Stevens Pass. And there's plenty of this Arkosic melange in the basement exposed north of I-90. Here's up by Mount Bering, views north from Mount Bering. And if you really restore all the strike-slip faults in the North Cascades and you get all this Arkosic melange back to where it came from, it is beautifully connected. This is the Western Melange Belt. It's beautifully connected to the Franciscan complex in westernmost California. There's more of the melange-type material down there. So these are rocks that have a long, far-traveled history, maybe even Baja stuff. And south of I-90, if we go to Mount Rainier, and this is the Goat Rocks, there's plenty of this beautiful Arkosic melange at White Pass, Ugly Russell Ranch. Grello all around this pine grass ridge, this Tiatin andesite flow, flowing over what appears to be a bunch of naked Arkosic melange, the basement rock of much of the Cascades. Okay, if we then get to the native cover, the youngest part of the basement, before we start our two stories tonight, we have a flat Washington. There are no Cascades. We don't have a Cascade arc. We haven't broken a plate yet. It's a mellow time, between 60 and 50 million years ago. But here comes Siletzia, about to wreak havoc in the Pacific Northwest. And we have not broken our plate yet. We have not broken our plate yet. And we've accreted Siletzia, and so geophysically we can see, if you can place yourself, this is Portland, Oregon right here. Here's Seattle, Washington right here. We can see that suture looking through all the young cover, and there's a healthy part of the real estate here that is accreted Siletzia bedrock. The effect of accreting Siletzia was locally profound, and if you look at the ridges around Bellingham, Washington, with a similar, just a simple air photo, it's maybe underwhelming. If you use LiDAR from Daniel Coe of Washington Geological Survey, you can see the elaborate folding of the Swak sandstone and shale, which up there is known as the Chuckanut sandstone and shale. And right from Gary Paul's house, Gary taking a photo, giving us a sense that that quote-unquote Chuckanut, which is an inside joke, he knows it's Swak, is right from his driveway, and we can see those originally flat layers have been tilted. Why? The accretion of Siletzia. So at the same time that we are tilting these Swak layers and these Chuckanut layers, we're breaking the plate way down below. They're tied. They're tied. A surface story and a now emerging subsurface story. So yeah, the Swak is everywhere in the high country. It's folded in many places because of the accretion of Siletzia. Siletzia is when we really start the action and we start setting the stage for breaking our plate. And we've done this a fair amount over the last few years, so I think I'm going to do the Siletzia part very quickly here. Again, Ken Clark getting us Siletzia offshore. Okay, we've got it, man. I think we've got it by now. talking to myself. But we finally break the plate. There's too much mass. Siletzia is too much basalt to easily just absorb and go down the subduction zone. It clogs the trench. And that ultimately is why we have a break in the Farallon plate. So as I was just saying, here's the folding of the Swauk and Chuckanut sandstones at the surface at the same time that we're breaking this downgoing Farallon plate. That's the model, that's the tectonic model, based on what? Based on the green line, which is the exact suture between Siletzia, accreted, and Old North America. And this red line is what? That's the Breakoff belt. These are the magmas that do not have a niobium depletion valley. These are the magmas that are bimodal. These are magmas that are found in a line. And they're the magmas that are between 51 and 48 million years ago. So here, from Jeff Tepper's students and Jeff Tepper himself, are some details now where we can find some of this Breakoff belt magmas. South to north, basalt of Summit Creek. Each of these are bimodal, by the way, so they're not only basalt, but there's also rhyolites associated with each of these. We're highlighting just a few. Summit Creek, Teanaway, Barlow Pass, maybe a little bit of Mount Pilchuck, I forget. And there's even some local stuff right above I-90 at Silver Pass. So side by side, I've been trying to do this with the chalkboard. Maybe you can see it now. This is the younger story. This is the older story. We have distinctly different magmas, and yet they're all in the Cascades. Come on, man, can I just say this? Before this winter, I've hiked up in the Cascades just like you have. You probably know more about the bedrock layers than I do. But I'm just taking pictures and going, well, I guess this is all just like old lavas in the Cascades, I guess. This sure is fresh air. I think I'm getting hungry. That's it. But now, if you can tease out these kinds of distinctly different stories with all of this data, that's really exciting to me, and maybe to you too. Yeah, so eventually we get the arc started. I think we're done with Ken's. Too many Ken's. Okay, all right. Okay, so precise ages. The mineral zircon has become very, very important for getting precise ages in these rocks. And not all bedrock layers have zircon minerals within them, but if you've got the zircon, it's super helpful. And the current Goat Rocks project, headed by CWU geology professor Hannah Shamloo, those folks up on the third floor are hungrily looking for zircons in those different mappable units in the Goat Rocks volcanic complex, to improve not only age constraints, but geochemistry as well. Okay, we've done our homework. It's easy now, I hope. Maybe we've set this up so it works. There's the Siletzia suture. Look at the linear Breakoff belt. Ellensburg is right in here. You drive up and over Snoqualmie Pass, you're doing this right here. Good. Mike Eddy, Purdue University, formerly of Massachusetts Institute of Technology, did a PhD, and he found a major unconformity, a gap in the rock record representing missing time, right at this 51 to 48 million year old time frame. So even in the stratigraphic columns across Washington, there's a major break just at the surface with these units, and we're tying it to a break in the subsurface with the broken Farallon plate. All of these are the Breakoff belt magmas. If you've been wanting some specific places to tie into this story, let's say you did follow the Breakoff belt story. Now, maybe you know some of these places, probably better than I do, with some new dates, some accurate dates. If we go up to Bald Mountain, the Bald Mountain batholith is part of this. I showed this photo last night. In tonight's lecture, Jeff Tepper is using the Bald Mountain Pluton and Mount Pilchuck volcanics, that's also Pluton, as part of the Breakoff belt, up to the north of here. And there's perluminous granite, another way to indicate that we have non-subduction related stories. The Pilchuck stock. Thank you, Gary, for the photo. No mafic enclaves. Come on now, this is the Breakoff belt. What are you doing? You can't be looking for hornblends or mafic enclaves. This is the Breakoff belt. We don't have hydrous minerals. We don't have water being added to the mantle wedge. We do not have this basalt injection into the base of the crust because there's no slab present when we're generating these magmas. Backcountry Lindsay Malone also here tonight. Lindsay contributed many, many beautiful photos also from the high country. This is still just the Bald Mountain Pluton, one of our selected spots. These photos are going to go quick, but I just want to give a nice visual tour of many of these beautiful places, both with the Breakoff belt and with the arc magmas themselves. Bald Mountain, adorable, adorbs. Pika pika. Barlow Pass Volcanics. Barlow Pass Volcanics. Yep, Gary Paul gets us up there. Jeff Tepper and his students never got to the Barlow Pass Volcanics. Maybe they will soon to collect more data. It's rugged country up there, but here's not just plutons now, but volcanic rocks as well that have this bimodal signature. They don't have that tantalum-niobium valley, a tuff near Independence Lake. Fine-grained rhyolite tuff, same thing. Beautiful photos. Accessible by foot traffic only, I think. Keep going. This is a place close to my heart. The Teanaway is a place to do easy day hikes here from Ellensburg, especially in the summertime. And so the Teanaway is a favorite hiking place for Liz Zentner and myself. Bimodal, part of the Teanaway story, part of the Breakoff belt. We see the feeder dikes of basalt, but there's also rhyolite within the Teanaway Formation. We're up by Blewett Pass, between here and Leavenworth, between here and Wenatchee. Many of you drove over it today. Beautiful feeder dikes on the old Blewett Highway. Why are those basalt feeder dikes there? It's the Breakoff belt. Like, I didn't know, man. I've been here 35 years. I did not know that story. And these beautiful feeder dikes are all linear. They're all parallel to each other, and the boundary between the Kittitas County and Chelan County. Rhyolite domes within the Teanaway, some of them back at the Breakoff belt time. Some of the rhyolites of the Teanaway are much younger. That's another story for another day. This is mapping done more than 100 years ago, by the way, by George Otis Smith. Schematic of the Teanaway rhyolite. This is many of the images from Jeff Tepper's students at University of Puget Sound. All these posters are on my website if you want to really dig deeply. Extension tied to the Teanaway rhyolite story. Beautiful breccias hosting gold, hosting Ellensburg blue agates. It's the rhyolites that are brecciated and have a story to tell. Look at this gorgeous Ellensburg blue agate within the rhyolite of the bimodal Breakoff. It's a drinking game now. You don't need me to keep saying the phrase. Okay? Photo from 1898. Photo from 2009. Ingalls Lake. It's still there. And where this all started, this Breakoff belt story started, Tepper and his student Lisa Kant went up to White Pass to sample the basalt of Summit Creek maybe 15, 20 years ago. And they were surprised that the geochemistry of this Summit Creek basalt was much more like the basalt of Siletzia offshore than it was the Cascades and the arc magmas. And so this is where this whole idea of a broken plate got started, because the geochemistry said a slab could not be present when we erupt the basalt of Summit Creek. Well, this past winter, many geologists were watching, including Daryl Gussie from the Forest Service, who knew the Goat Rocks area quite well. And Daryl started wondering during the episodes, I wonder if my basalt of Discovery Creek is the same as the basalt of Summit Creek. I wonder if it's also something we can add to the Breakoff belt magma story. So he shared by email with Jeff Tepper and Hannah Shamloo at Central some of his field photos of the basalt of Discovery Creek, brought some samples in. Hannah Shamloo collected some samples, and the Goat Rocks team started to work on the geochemistry. And I think Hannah, as she's watching Severance or something, is also plotting up data at the same time in her living room, the same kinds of plots we had on the black chalkboard. And that basalt of Discovery Peak, no valley for the niobium, ding, 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 we have a Breakoff belt magma. So we can even add to our collection of field sites in the Cascades beyond what we have now as more geologists share their data, share their samples, and we have young professors like Dr. Shamloo doing more work along these lines. Oh yeah, look at that plot. No idea what it means, but I suppose it means bimodal. So that's the end of our Breakoff belt story. I think we're comfortable. I hope we're comfortable. For the rest of tonight, we're going to transition to the arc magmas, but we need a visual to explain a side effect or an interesting development tied to the Breakoff belt. And that also is Jeff Tepper's work out in eastern Washington, and even some magmas of this vintage back to northern Idaho. I'll do this quickly because it's not the main part of tonight's message. But these chalice magmas, these Kamloops magmas, these magmas that are at the time of Siletzia, between 55 and 46 million years ago, are blotchy and scattered across the Pacific Northwest. If you were with us last night, we speculated that these magmas here, tied to extension, might be tied to events happening on the opposite side of the Pacific Ocean. If you remember that part of the story last night, that's what we're talking about right now. But Tepper and his different students were out in eastern Washington visiting granites and other plutonic igneous rocks in northeastern Washington at these counties. This is up north of Spokane. This is east of the Grand Coulee. And look at their new dates in the right column and how precise they are compared to the old dates that we had for many of these plutonic igneous rocks of eastern Washington. Do you see what I mean by just getting more precise dates can pinpoint a story? We no longer have dates of plus or minus 1.5 or 2.5 million years. The precision of this age dating is robust currently and will continue to improve. So with that precise date story, Jeff Tepper and his students then were able to realize that there's an age progression from northeast to southwest. These are numbers in millions of years, roughly 52 to 46 million years ago. If we peek beneath the much younger Columbia River basalts, there's a lot of this Eocene igneous rock activity. This is the one I wanted to show you. So these are granites at Grand Coulee Dam. These are plutons at the North Cascades Highway, Golden Horn, Cooper Mountain batholith, and others, and including these bedrock units up here in extreme northeastern Washington, which I know nothing about. But Jeff Tepper's been up there with his students in this 52 to 46 million year old age range, got Tepper thinking about a tectonic model that might somehow tie to the Breakoff belt that we've been focusing on tonight. How do you explain this age sweep? 52 to 46, northeast to southwest. And yes, it culminates at places like Liberty Bell and the Golden Horn magmas of the North Cross Highway. And up until now, I would just look at these two peaks and go, yeah, I guess they're both made out of granite. I guess that's the end of the story. And now you realize that the Black Peak batholith is twice as old as the Golden Horn, and the Golden Horn is from crustal extension from stuff happening on the other side of the Pacific, and the Black Peak batholith probably came from Mexico. I mean, come on, man, there's stories all over the place here, not only with ages, but chemistry. This is all up at the North Cascades Highway at Liberty Bell with stunning photographs from Gary Paul. But it's this rollback story that I caught wind of at a geology meeting hosted by Jeff Tepper at his poster there in Portland. And that rollback, which you're about to see with a brand new animation, culminates at Saddle Rock above Wenatchee, Washington. That's part of this rollback story. So we're heading finally to the Idaho slab curtain, and we're looking at cartoons of accreting Siletzia, and now in purple, you can see this underground piece of the broken Farallon plate that's hanging vertically underneath Idaho today. The size and length and width of Siletzia, the size and length and width of the slab curtain, are they connected? Here's a tomography image from Gene Humphreys showing the Cascades, the subduction of the current Juan de Fuca plate in blue, and here's our detached broken plate, which used to be here, but has found its way in some sort of grand choreography to end up vertically to the east. More tomography where we can see the slab curtain underneath Idaho and the broken Farallon plate, which south of the California state line continues quite a bit to the east, but it's been broken here. Imagery looking through with X-ray glasses down through the crust of North America to see this irregularly shaped former massive Farallon plate. This is the place where we broke the plate, right here. So that tomography works well. And by the way, Tepper worked on this Breakoff story before he saw this imagery from Spencer Fuston and got very excited when there was a nice correlation with the geochemistry story, the igneous petrology story, and this brand new tomography data from Spencer Fuston from Houston, Texas. Put it all together, and we need an animation. So some of you are aware that I like to do live programs on YouTube, and every winter I have 26 episodes with a theme, and this past winter was the Cascades. And many of the viewers watch regularly, and I'm very grateful for that, and some of the viewers decide that they want to go a couple steps beyond. They want to help out somehow. And so the photos from Gary, that was a way to help out the learning community. The maps from Tom, the photos from Lindsay, and many, many others. Not just this past winter, but other winters as well. It's a nice community. But early this past winter, in November, I said, I think this alphabet, this Cascades A to Z, is going to be a visual feast. And maybe you artistic types, you visual types might be able to contribute your talent somehow. Maybe even we'd have somebody who has experience with animation that could help us with something like this, because many of us can't quite see it. And so Paul from Kashmir, would you stand up for just a second, Paul? Paul from Kashmir. I didn't know Paul. I met Paul for the first time just a few minutes ago before we started. Paul, by email, said, I think I can try this, if you're willing to give me a little time. And I said, I got lots going on, Paul. He said, would you just check? And I said, could you just, here's Jeff Tepper's email. Can you just work with Tepper and see if you guys can come up with something that works? And so Jeff Tepper and Paul from Kashmir have gone back and forth countless times to create a brand new animation that was a direct result of our learning together, all of us, this winter. And so to complement these photos from this 2019 poster from Jeff Tepper, and breaking the plate, and also rolling the thing back. Oh, there you are, Paul. Can I share with you, please? We'll look at it twice. We'll just put it on a loop, and we'll just let this thing play. We accrete Siletzia off the left side. We have our first break over here to the east of Washington. The magmas are starting to pond. This plate, the Farallon plate, is starting to droop. It's starting to roll back. And here's our age progression starting to work its way from 52 to 50 to 49. And now at the same time, we do our big break that we've been talking about tonight, underneath the Cascades. And so now we've broken this Farallon plate twice. Here's the Breakoff belt magmas with no slab beneath, and here's our rollback, giving this beautiful age progression, 52 to 46 million years ago at Wenatchee, Washington. And again, there's sound on this, but we don't have the sound turned down, so Paul, sorry for cheating you there. This is the kind of thing that we can do together. This is a whole group of people with different levels of expertise, but we're all learning as a community, and these kinds of experiences, and I don't know how many hours this took you, Paul, but I'm sure that we will all really enjoy using this in our classrooms. Jordan Carey in particular will be teaching Geology 101 for many years in the future, and we'll be using this animation over and over because it explains so much about the igneous geology in our state. Age progressions which everybody can follow, and the topic of tonight, a broken plate beneath the Cascades. Thank you, Paul. All right. We transition finally, very quickly, to a march through some of the arc magmas, and then we'll wrap it up tonight. At the beginning of the arc magmas, remember now, we have our trace element signatures that are very, very different than what we had with the Breakoff belt magmas. I think it's important for us to see those plots professionally, and then go to some of these true arc stories as well. This is what a true valley looks like with tantalum and niobium. This is an arc magma signature. Again, students at the University of Puget Sound. And Chris Mattinson from Central Washington University says, you know, Nick, I think I can help explain why the arc magmas have a valley or a depletion of tantalum and niobium. And he sent me a nice simple email that even I could understand. Chris says, look at these thin sections of rocks that are arc magmas, and there's a mineral called rutile. I appreciate your general audience-friendly explanation of arc rock spirograms in yesterday's show. In case it's helpful, I have a visual for why the niobium and tantalum are relatively depleted in arc rocks. The orange mineral is rutile, which contains nearly all of the niobium and tantalum in typical eclogites. And the niobium and tantalum stay locked up in the downgoing slab and don't end up in the arc magmas. So you're basically trapping the niobium and the tantalum in these little rutile guys, and they're in the eclogite, which is in the heavy end of the tablecloth, going in the end of off the edge of the dining room table. And so we're not allowing those two precious trace elements to get into the arc magmas that are rising through the crust. And yet when we look at a Breakoff magma, there's no valley because we don't have the subduction. Back to a depletion and a valley. Back and forth between arc magmas and Breakoff belt magmas. If we start traipsing around in the Cascades looking for arc magmas, maybe you know some of these places. We're going to go very quick now. Let's visit the Gobel volcanics, the Northcraft, the Tukwila, and Mount Persis in France. These are all arc magmas that are in the early days between 46 and 40 million years ago. But by now, we have a subducting Farallon plate, and we're generating these arc magmas. So what are these photos? These are more viewers. Olympia Gary, never met him. He's like, I just went down to the nearest quarry, and I looked up a geologic map, and I've got some photos of the Gobel volcanics. These are early days of the volcanic arc. More contributions, heartfelt contributions from the viewers. To me, it's just another lava. But if we have the context, places like the Gobel volcanics are important. Down in southwestern Washington. Thank you, Olympia Gary. Jeff in Tacoma, a.k.a. Jeff Tepper, is also contributing Gobel volcanics 41 million years ago. Mafic enclaves, you bet. Hornblende, you got it. These are arc magmas because we've started the subduction zone, and the Farallon plate is diving beautifully beneath the present volcanic arc. Geology field trips galore to all these spots with all of these impressive deposits and layers that are often overlooked. Marching north to the Northcraft, now we're, I guess, in the Chehalis area, south of Olympia, heavily forested. More shots from Olympia Gary. This is all inspired by our episodes this winter. Many of the viewers on the days off between programs will go out and start snapping photos and emailing them to me so that I can share them with everyone else. If you don't have the framework, I'm speaking for myself, if you don't have the context of the framework, I lose interest pretty quickly. But if we can establish a framework to hang a bunch of these details, then suddenly I do have interest. I'm not that interested in detailed mineralogy or all sorts of other minutiae, but if I know that the Tukwila, which is near the SeaTac airport, and the Issaquah Alps, if I know that's part of these early days because we've already broken the plate and we've now driven and sucked the oceanic Farallon plate deeper. That's right, I said sucked. That's coming down the trench and the Drunken Charlie Complex, Jeff and Duval sending photos. We can just go on. And now we can look for key minerals. Do you remember what we're looking for in these rocks to prove that they're arc magmas? I hope so. Mafic enclaves and hornblende. From the videos I did with Jeff Tepper last summer, here are some of these mafic enclaves where we're injecting liquid basaltic magma into the magma. And here's this tiny hornblende that we found impromptu, back to the mafic enclaves, back to Granite Falls, arc magmas. Those aren't just dark rocks that fell into the magma soup. Those are squirts of Hershey's chocolate syrup that then exchanged elements back and forth. Back to the hornblendes. You get the idea. There is some hand sample geology that can be done. To the Issaquah Alps to share some of Tom from Maple Valley's photographs. We're now in the Issaquah Alps, just south of I-90, between North Bend and Seattle, Washington, near Lake Sammamish. And now we're like in civilization doing geology. Tom's right along Highway 18 with all the construction by Tiger Mountain, and he's drilling into these early days of the volcanic arc. Photo after photo, map after map, using GIS, using the Washington State Geology portal. Viewer Tom was doing heavy lifting for us through much of this past winter. You know, garbage right on the side of the road, and yet we've got Tukwila Formation to look at. And there's many new stories to pull out of these rocks as well. These are rocks that probably have major stories that we don't have yet because we don't have the geochem to the level that we need it, or the precise dates. And maybe tomography too, I don't know. So some of you are from the west side and know these beautiful places, and sometimes not so beautiful places. And as we work our way finally to the north, we get up to Mount Persis by Mount Index, we have more of these early days of the volcanic arc. Lindsay from Seattle chiming in with the Fuller Mountain plug. And all sorts of plutonic rocks that work as well in this area from the Washington Geological Survey, Joe Dragovich and others. One of the first places I visited in August with Jeff Tepper was to Tamanous Rock over by Port Townsend. And these Ken Clark drawings that I keep showing were custom made for a roadside exhibit right at the crossroads in Chimacum, over there near Tamanous Rock, which is available publicly now to view. These sketches are showing Chimacum and the importance of Tamanous Rock, which is one of the earliest Cascade volcanic arc magmas to show up in this crop. And Tamanous, which some of you know, has many geologic stories to tell, including adiabatic signatures within that material at Tamanous. So I think we've got it now. We've seen these sketches over and over and over, including breaking the plate beneath the Cascades to start the Cascade volcanic rock. And I want to publicly thank Tom. Would you stand up with your work here, please? There's Tom in the back. Lindsay, stand up. Glenn, helping out all through. There's Lindsay. There's Glenn in the front. And backcountry Gary Paul. Backcountry Gary Paul, everybody. Thanks, everybody, for coming tonight. Thank you so much.